Hello and welcome again to my Physics Online video lecture series. In today's video I'm doing just a brief continuation of my previous video about self-induction. This video is just to focus on self-induction for three basic geometries: the solenoid, the toroid, and the coaxial cable. The point is not to go through a rigorous derivation per se, but simply to give you the results for these three. So in some sense this is like a supplement to my previous lecture about self-induction. You will recall that we have both Faraday's law, which govern induction. That's the one that says that the induced EMF on average should look like negative of the number of turns times the rate change of the magnetic field flux per unit time. And so that often is negative in delta of B dot A, where A is the cross-section area for which the flux is being calculated, over delta T. So this is like a cross-section area. And so that is Faraday's law from an algebra-based perspective. The other thing that maybe I have introduced is inductance. So inductance is sort of like the measurement of an object's tendency for being receptive to induction. And this inductance was defined in such a way that we could sort of replace these weird rate change of fluxes with instead a simple inductance term times the rate change of the current passing through our device, rather than figuring out magnetic fields. So this right here, this would be self-inductance, or if you have two objects, you'd have maybe an M for mutual inductance. So what we're doing in today's video is just simply stating the result for this term right here. L is sometimes formally called self-inductance, but I will often just call it the inductance. It's the fundamental property of an inductor in much the same way as capacitance is the fundamental property of a capacitor, EMF the fundamental property of a battery, and resistance the fundamental property of a resistor for circuit purposes. And so this, in some sense, actually defines the inductance. We want to do something similar to what we did with capacitors and resistors, wherein we figure out what the inductance is based on actual properties of the thing that is acting as a self-inductor, say a solenoid or what have you. If I have a solenoid with axial length L, in turns of wire, and let's say turn radius R, then it would follow that the magnetic field within the solenoid, B, should look like mu naught times the number of turns per unit length, N over L, times the current passing through it. So this is in some sense like recall from Ampere's law. Using the definition for magnetic flux, phi sub B must be B dot A, so that would be B times A times cosine of angle between them. This number right here is 1 because it's a 0-degree angle between the A vector and the B vector. And the area, of course, would be the area of one circle, so that would be pi r squared. So I have pi times r squared times B. Now, what's the rate change of the flux if I change the current? Well, delta I over delta T would produce a delta B over delta T. Specifically, we could say something like delta B over delta T is equal to mu naught N over L times delta I over delta T. In other words, we're not allowed to change the number of loops or the length, axial length of the solenoid. We can only change the current, and that's what is producing the change in the magnetic field. It follows that the rate change of the flux, in other words the EMF, which should look like N times A times delta B over delta T. That's your Faraday's law. It follows that this EMF, if we combine this equation with this equation, will look like N times A times mu naught times N over L, so N divided by L, times delta I by delta T. Now we can combine these terms right here to be the self-induction, because what's left over is the delta I over, whoops, this should say delta T. And so L, if we plug everything in, looks like mu naught times N squared, the number of turns on the coil squared, times pi r squared divided by length. Again, the self-inductance for a solenoid, mu naught, the fundamental constant, permeability of free space, times the number of turns squared, this is number of turns, times the cross-section area of the solenoid divided by the axial length of the solenoid. And so if we assume a circular cross-section, you end up with the second equation, pi mu naught N squared r squared over L. So a circular cross-section for solenoid will give this. And so this equation is just specific to solenoids. Now I'm not going to derive the equation for the coaxial cable or for the toroid. Those usually involve a bit of calculus. However, we will supply the result for both. All right, so 3 configurations. What's the self-inductance for each? Well, obviously for the solenoid we already have the equation. It's mu naught N squared A over L. For the toroid, it's actually pretty similar. We just replace the L, the lowercase l, with the effectively circumference of the thing. So we could say mu naught N squared A over C, or if you prefer, mu naught N squared A divided by 2 times pi times r. For the coaxial cable, the self-inductance actually needs to take into account the 2 relevant radii of the cable as well as its length. For this one, I need kind of 2 diagrams to show what's going on. There's sort of your coaxial cable as looked at from the end on, and so this right here would be 2 times the inner radius, so this is your inner radius, and then this distance right here, this would be your outer radius from the center of the coaxial cable. Basically you have a ring embedded, you have like a wire embedded in a extruded ring, and so this would be like end view, and viewed from the side, again, this would be 2 times the outer radius, and this inner wire right here, the diameter is 2 times the inner radius. So we could call that RIN for inner. And then the wire itself has length little l. So that's your coaxial cable. Compare that to your solenoid, which is basically like a bar that you've wrapped a bunch of wire around. So you have a length and you have a cross-section area. A toroid is like taking that same thing and bending it into a donut shape. So you have sort of like a donut radius, and then you still have a cross-section area. And so that's what your self-inductances depend upon. Let's finish with a quick example. All right, so we have a toroid, and we want to determine what its self-inductance is given some basic parameters of the toroid. So we can use our equation that says that L should be approximately mu naught times n squared times A divided by C. And so that is mu naught times n squared times pi little r squared divided by 2 pi big R. Notice that these two r's are not the same. And again, this one right here, this is your axial radius, this would be your big R. This is your cross-sectional radius, this would be your little r. And this 35,000, this would be your value for n. And of course, parenthetically, you know that mu naught is 4 pi times 10 to the negative 7. Right. So we would want to then plug in the numbers from above. So you've got your 4 pi times 10 to the negative 7 Tesla amp per meter times n squared. Let's call that 3.5 times 10 to the 4 squared. And then, of course, you have your pi. The pi's actually could cancel here. You got your r squared. That would be this little r, or 0.10 meters, and square it, and then divide by 2 times the 0.25 meters. When you plug all that into your calculator, you get about 61.575, so we would maybe round that to two significant figures and get about 62 henries. And yes, Henry is the correct MKS SI unit for self-inductance. Well, that's all for today's video. Hope you learned something in it, and as always, thanks for watching and farewell.